All right. Now then, if you look in your text, we are on page 601, and we got some practice problems there. So, oh boy, I love practice problems, Mr. A. That's right, Mr. Beer likes to be happy physicist guy there. Number one, a car battery causes current to flow through a lamp. Okay, so let's draw the picture. I'm going to draw it schematically, right? So I use that funny word called a schematic, and it's just basically symbol representations for electric circuits. Well, a schematic could be a schematic of anything, but commonly it's electric circuit. Okay, so this is a 12-volt battery, and current flows from positive to negative. We learned that when we were talking about electric fields. We always go from positive to negative, and this is our light bulb right here. Okay, so we have a 12-volt battery, and we're told that 2 amps is moving through the circuit. What is the amount of power used? Okay, so power is equal to I don't know what. But we do have an equation for it. It's IV. That's our boxed equation here. And then that would be 2 times the volt, 2 amps times 12 volts. Let me see. Do I know what that is? Yes, of course I do. I'm graduating high school. I can do that. 24 what? Let's see. What is the units for power? Watts. What you say? 24 watts, right? Okay. That's right, because energy is joules, current is in amps, 24 watts. Okay? Well, that was an easy one, Mr. A. You know, I could do these physics problems all day long. You know, I don't know why I procrastinate and don't do this stuff. It's kind of fun. I don't have anything else to do. I'm in quarantine, for Pete's sakes. Okay, number 2. What is the current flow? What is the current? So that's our question, first of all. And then we are told the power, 75 watts, through a 75 watt light bulb that is connected to a 125 volt outlet. Okay, does that equation still work? Well, we might need to rearrange it a little bit, right? But hey, you guys passed algebra, so we just need to solve for I. I is equal to P divided by V, right? So if I give you, if you know any 2 of these, you should be able to find out the third, right? And then, you know what? Here's a gimmick, right? I do this for my freshmen all the time. So P I times V, right? So we don't know what the I is, so you cover up the I, and it's P divided by V. See how slick that works? That might be something you want to write down in your notes, okay? So we're given that the power is 75 watts, and then we divide that by the voltage, 125 volts. Make sure that you are using, if you're going to use standard equations like this, you need to use standard units, all right? So grab my handy-dandy calculator because I can't do that one in my head. 75, oops, not divide, 70, not times, 75 divided by 125. Okay, 0.6 amps, 0.6 amperes. Okay, all right, chugging right along here. I want to do number 3, and then I think that's all I want to do out of this set. Okay, this one pulls in the energy equation, so we're gonna use this one. So question number 3 is, the current through a light bulb connected across the terminals of 125 volt outlet. So voltage is equal to 125 volts. The current is 0.5 amps, 0.5 amps. At what rate? Okay, what are they asking me for? Okay, so we need to decode that. At what rate does the light bulb transform electrical energy into light energy? Okay, well, sounds to me like they're talking about energy. No, energy is the potential to do work. Power is power. This is where it power is a rate. So when it asks you something about the rate of energy flow, then you need to know that we're talking about power. So at what rate, that is the secret code word for power. At what rate? Okay. Power. Okay. So we do have a formula for that, which is equal to I times V. Oh, and good. That's what we're told, right? So that turns out to be a real simple problem, except for they didn't explicitly tell us that we wanted power, right? So that would be 125 times 0.5. Okay. So 125 times 0.5 is equal to 62.5. And we are talking about watts. All right. So now, that didn't pull in this energy equation. So let me just embellish just a second. So this current through a light bulb is, it's a 60, basically, let's just call this a 60-watt light bulb, okay? It's a 60-watt light bulb. Here's my light bulb, and that's a really, really bad light bulb, okay? 60-watt light bulb. How much energy does it take to power, that's not a good word, to light? I don't want to use that word because we have a very specific meaning for the word power now. How much energy does it take to light the bulb for 60 seconds? Okay. Now we can use this equation. Energy is equal to PT. Right. So if it's a 60-watt light bulb and we're going to run it for 60 seconds, 60 times 60. Oh my gosh, I should be able to do that in my head. 6 times 6 is 36 and two zeros. 36 and two zeros. It's going to be 3,600. Energy is measured in joules. Okay. So let me clean this up a little bit. Energy is equal to power times time. Okay. How much energy? Okay. All right. So those are the kinds of examples that you're going to encounter in the first part of chapter 22, section 1. There are some practice problems on page 603, and they're going to ask you to draw circuits. What I want you guys to do is to, instead of doing those, what I want you to do is I'm going to close this thing here, and I'm going to go to this simulator right here. What I want you guys to do is to play with the Circuit Construction Kit. I've linked this in the Google Classroom. It is based on HTML5, so it'll run on any browser. And what I want you guys to do is to build a flashlight circuit using batteries and wires, and I want you to connect them in a way that I want you to have nice, I always like to make nice 90-degree angles with stuff. So I'm going to do this. This is kind of fun to play around with. I wish I had this when I was a kid, because it's just, you know, call me silly, but, you know, I just kind of get into these things, right? So you just kind of drag and when they get close to each other, you can stretch them, they can connect. And I'm going to put a little switch here so that I can turn my light bulb on. So you can close the switch. And looky, can you see the electrons flowing? You can see the electrons flowing. And look, the light bulb's lighting really bright. And then you've got, you can turn on the values. And for a 9-volt battery and a 10-ohm light bulb, you can actually calculate what the current flow is. Or you can measure what the current flow is, right, with a little current flow meter. And you can measure the voltage across the lamp if you want to. So this is a real cool thing to do. So of course I have 9 volts across the lamp because I've got a 9-volt battery and there's nothing else in the circuit, right? So this is a pretty cool thing to experiment with. And this is actually a flashlight circuit, right? This is actually how a flashlight works. So I want you to experiment with this. Now watch. If this is kind of like a more realistic view of what a battery looks like and what wires look like, but click this button and it looks like a schematic, right? So you kind of put that away, close out some of these values and labels, show electric current. That is what I draw when I drew my circuit, see? So there's a schematic representation and a real representation. So the kinds of questions that are on 603, I want you to use the PhET sim. Don't waste time with pencil and paper when you've got a really cool PhET sim to use to answer the practice problems on page 603. Okay, and then that will bring us to talking about Ohm's law on page 604, and that's where I want to kind of break up this section 1 because Ohm's law is a lecture all in itself, and I will spend a fair amount of time doing that. But I needed to go back and talk about energy and power in context of current flow, and because we were used to those terms when we were talking about kinetic energy and potential energy and those kinds of things. It's kind of a new way to think about it when we're talking about electricity. But energy and power are terms that apply to whether we're talking about electrical energy or whether we're talking about mechanical energy. So I wanted to make sure that I got you up to speed onto that. And now that our brains are really clicking on what an electric circuit is, it's just a pathway for current to flow. Now we can start talking about Ohm's law. But that'll be another lecture. Okay? Okay, so I'm going to stop the recording now, and you have what you need to know to go explore on your own.